Section 2.1 is basically the groundwork for all of what we're going to do in Chapter 2, very much so. It will feel like the most challenging section because it has the most details to it, the most work, honestly. It will have the most work. So what I want to bring to your attention is something we've actually hit on and talked a little bit about before, and it's secant and tangent lines. So I'd like to draw a picture, and you've seen me draw this picture we did on the very first day of class, where it looks something like this. And I'm going to mark, actually let me get a little bit more detail on here before I mark anything, or before I copy and paste it. We're going to call this point C. It doesn't really matter where you put it, just put it on, roughly in the same general area is fine. And we want a point that's a little bit of a distance away from C, so it's a distance h away, so we're going to call it C plus h. So that point is right here. So if I want to take the secant line through those 2 points, I'm creating a line that will cut through both the points that I've identified. Okay, give me a second and I'll shift my line. That'll work. And this would be considered our secant line. A couple of things over here is you could definitely find the slope. This right here is f of c, and the point right up here is f of c plus h. Right, they're the y values that correspond with those x values. And if we were looking at the slope of the secant line, we would take those two y values and we would subtract them. We would take the two x values and we would subtract them. And we would end up with the y values staying the same on top because there's no way to manipulate that unless I have an equation given. And in the denominator, you see that the c's will add to 0, so I'm just simply left with the h in the denominator. And this is the slope of the secant line. Okay? And h is really just telling you how far away the two x values are. Now what we want to do is we want to take this same image and we want to let our h value get closer to the c. I shouldn't say that right. We want our c plus h value to get closer to the c, or the h value to get smaller and smaller as we go. So instead of the h value ending where it did before, maybe it's half the distance it was before, some portion anyway. And so instead we have this particular point. And we find a different tangent line. I'll try some different colors here and see if I can get them to work out nicely for us. So we have my purple tangent line now. And then we let the point get, again, a little bit closer. So I don't have to half the distance, but visually speaking, it's easier for me to do that maybe than just estimating. So the point gets a little bit closer to that point at C on the curve, and we'll draw a blue line. Sorry, when I draw my line, it's kind of hard to control where it starts and stops, so that's why I keep shifting it. And so what happens is that these lines are getting closer and closer to the points. The points are getting closer and closer to the point C, which means that our slopes of our lines are getting closer and closer to the slope of what we call a tangent line. So this idea of making the h value get infinitely small is exactly what we need in order to define the slope of a tangent line. So the slope of the tangent line, if f is defined on an open interval containing c, and if the limit as h approaches 0 of f of c plus h minus f of c over h equals m exists. So this should look familiar. I didn't have a box. Right? That was the slope of the secant line that I did just a minute ago. So the slope of the secant line is embedded inside of this definition. But what we have inside of there as well, new, is we have this limit notation, and it actually ends up equaling a specific numerical value. Okay, over here, I didn't have the ability to say that it equaled anything per se because the h kept changing and I didn't know what it would be. And over here, although it's changing, it's approaching 0. And eventually, if it exists, the limit will actually be a constant number, m. We'll talk about when it doesn't exist at the very end of today because there are a few places where it won't exist. So then the line passing through CF of C with slope m is the tangent line to the graph of f at the point CF of C. the slope of the tangent line to the graph of f at the point C. F of C is also called the slope of the graph of f at C. Okay, so we're talking about it, we're giving very similar names, and it can be a little bit messy because we've talked about slope of several things. There's a slope of the secant line, that's over here, and it does not have the limit notation. But once we put that limit notation in, it's the slope of the tangent line, or we can also call it the slope of the curve at that particular point. Slope of the tangent line and slope of the curve mean the same thing. So what I want to actually show you how to do is how to go through this process to find these limits. And I'd like to show it to you two different ways, and you can pick which one you like better. So different resources that I use actually show it different ways. Different times I've taught it different ways. So I'm just going to show you guys both of them, and you can pick your favorite. Sound good? Okay. So the first option is to simply start with the exact equation that we just had on the previous slide. So it's the limit as h approaches 0 of f, except that this one's g because my equation's g of x plus h minus g of x over h. Okay, so we're just writing the equation down that we had on the previous slide, not the equation, but the expression, the definition, with the letter g instead of f. So this is sort of one option of how we can do this. If we do this, you'll notice that this g of x is exactly this equation here, right? So I can simply take the orange part that's highlighted at the top, and I can replace it into the limit definition for the part that's orange highlighted at the bottom. So I'm going to skip a little space as I do that because I don't have the other pieces. I'm going to continue down the line because I want to put the comparison on the other side so you can see it for my other option. But you could definitely put equals and continue on the right-hand side. You still need to put limit, because until we actually evaluate 0 for h, right, like substitute it in, we have not actually eliminated the limit. So we have not done the g of x plus h part, but the g of x itself is 6 minus x squared. So you get that for free because that's given to you. The equation's always given to you. Now the other part, g of x plus h, means that the substitution kind of goes the other way. I need to take this x plus h, and I need to plug it in for x into my equation. So the same equation, 6 minus x squared, except it doesn't have the x where the x is. It has x plus h where the x is. So I have that same 6 minus, but now I have x plus h squared instead. Okay, so these two should look similar. This and this should look exactly the same, except that where one of them has x, the other one has x plus h. Okay, so far so good. Everything we do after that is algebra. We're simplifying the algebra that's involved. So some of these things that I do, if you feel like I didn't catch that, it might be because maybe you haven't had an algebra class in a little while, or maybe your algebra skills are just not your strongest skills. Okay? So as we do this, if there's struggles that you're having with the algebra, you might need to come and see me or to go to the Success Center and ask some questions about the algebra that's being involved. Now I'm going to leave the 6 minus here. This x plus h squared has to be FOILed out. It is not x squared plus h squared. It is x plus h times x plus h. I'll use this space over here as a reminder just for the moment, and then I'll erase it. We have to FOIL this. And when we do FOIL this, we end up getting, and I'm going to put this still in parentheses because that negative in front, x squared plus 2xh plus h squared. Okay? And then I'm going to go ahead and distribute this negative through because there's nothing to clean up inside these parentheses. So I've got minus 6 plus x squared all over h. So hopefully you notice there's a 6 here and then there's a negative 6 here. Yeah? Those are definitely going to add to 0, and any constants will always do that. So anytime you have a constant involved, it's going to cancel itself out when you do this subtraction in the numerator. The negative through here, I'm going to go ahead and distribute it. I've got negative x squared, negative 2xh, negative h squared, and then I still have that positive x squared at the very end, all over h. Again, still writing limit because I still have not evaluated h as 0. So what do you notice on the top now? Yep. Just like the 6, I've got a negative x squared and a positive x squared, so those add to 0. I'm going to go ahead and write it one more time, although I think at this point you probably could not write it and it would be perfectly reasonable, but just since it's the first time I've done it, I have negative 2xh, negative h squared, and over h. What you should notice at this point, always, is that there's an h in every single term. If there's not, you've got an algebra mistake before this. Because what should happen is that h in the denominator that's causing the denominator to equal 0 should cancel out with every term's h in the numerator. So you can think of it either as canceling like this, which works just fine, or if it helps you to think about factoring this out, I have an h here, and I can take it out. I've got negative 2x minus h in the numerator over h. If it helps you to think of it like that, you can do it like that. It doesn't matter to me. They're equivalent processes, but those h's cancel. So I've run out of space a little bit. Let me shrink a few things. Try one more thing. So I still have my limit notation. I'm almost not to have it. And I have negative 2x minus h. That's what I have at this point. Now I can actually stop writing limit, and I can plug in the h as 0, not x, but the h as 0. And I get negative 2x. Now this is in general. In general, I get negative 2x. But they told me up at the beginning on this particular problem, they don't always, but on this particular problem, they actually told me to evaluate it at a specific point in time, namely x equal to 1, right? So I'm actually finding this at x equals to 1. So I'll just note that this is when x equal 1. This would be negative 2 times 1, or negative 2. So my solution to this particular problem is actually negative 2 because they gave me an x value. If they didn't give me an x value, you would just leave it written, generally speaking, as negative 2x. And then you could use it for any x value that you'd like. So one of the draws, the appeals of this particular method is that every step is equal to the next step. Okay, that's something that's appealing about this. One of the maybe drawbacks to this method is that it's a lot of writing, number one. I mean, there's a lot of steps that are written here. I get to write limit a whole bunch of times, like an insane number of times, right? It's crazy. And then I also have to keep track of several different operations at the same time. Namely, I had to do the operation where I plugged the x plus h in while I was trying to do subtraction and division and the limit all at the same time. So there are some good things and there are some bad things on this particular method. The other method actually is called the four-step method. So let me show you what it looks like. And then after this, you can use whichever method you would like. So what the four-step method does is it breaks this definition of limit, which is now all messed up in how I've written it. Limit as h goes to 0 of g of x plus h minus g of x over h. And it breaks it down into 4 steps. So I'm going to highlight the 4 steps for you. The first step is the orange step that I just highlighted. Okay? You just do that part only. Step number 2, we do the whole numerator. And that's your second step. So you take what you did from the first step and then you combine it with the rest of the numerator. The third step is to take all of this. So you take everything you did in the numerator and then you divide by h as your step number 3. Right? You're processing through it sort of not exactly in a cycle, but in a methodical way. And then your step number 4 is the part with the limit. So let me show you how that looks. It's going to be all the same algebra that we just did. It's just going to be in steps. So as you're doing this, you do need to keep in mind that all the steps are not equal to each other, like it was in the last problem. Right? The first part of the way I did the problem, every step was equal to the next step. So you had to have the limit written every single time. You had to have all the pieces written every single time. If you're doing the 4-step method, you need to label your steps because they're not all going to equal one another. You're going to have step 1, and it is not going to be equal to step 2. Step number 1 is to find g of x plus h. So it means to take the equation that we were given, which was 6 minus x squared, and substitute the x plus h in for the x. And then we're going to do the algebra on this step. So as we do the algebra on this step, I have 6 minus, this is x plus h times x plus h. You don't necessarily have to write that out. If you know what that is, that's okay. I'm going to combine the next two steps where I distribute and I multiply through by the negative. So that's going to give me negative x squared, negative 2xh, and negative h squared. Show more steps if you need. But that's what g of x plus h is. And at that point, I'm done with step one. In fact, I'm even going to draw a line here so that it's visually separated for you. Step number two, then, is to take that same g of x plus h that we just did and to subtract the g of x. So I'm going to rewrite 6 minus x squared minus 2xh minus h squared. And then, actually, let me do this. I'm trying to give myself just a little bit more space. And then I need to subtract the g of x equation. So minus 6 minus x squared. The nice thing at this point in this particular part is that if I haven't distributed to the negative, I don't even actually have to, because everything in that last set of parentheses has to cancel with something before it. How do I know? Well, because it doesn't have h's in it. That's really it. It's got to. And it does, right? I've got a negative 6 right here, and I have a positive 6 up here. I have a negative x squared here, and when I distribute that negative to the negative x squared, I get a positive x squared. So things reduce in step number two. They always do. I'm left with negative 2xh minus h squared, and that's it. So step number one expands things, and then step number two cancels stuff out. Step number three cancels things further. It takes the same g of x plus h minus g of x, right, from step number two, and it divides by h. So it takes that negative 2xh minus h squared, and it divides by h. So again, I can think about the division whatever I'd like. I can either cancel each individual term, which is fine, because they all have h's in them, or if you prefer, you can factor it out. I'm going to show you the factoring out this time just because I didn't show it fully last time, and so if you want to do it this way, I'd like for you to see what that means. If I take the h that's in common out of the numerator with the h in the, and then I've got the h in the denominator, then these would cancel like that, and it would leave me with negative 2x minus h, if you like that way. Okay, what I meant to do. Okay, step number 4 is the limit step. So I only have to write the limit part in step 4. That's a pretty nice feature of this. The limit as h approaches 0, and it's going to be whatever I got in step 3. So that was negative 2x minus h. So in this step, limit actually gets written right here in this one little spot. And then over here, I would actually be able to evaluate h as 0, so negative 2x minus 0, and I get negative 2x. And of course, just like I did before, because I'm given the x value, I am able to plug in at the very end when x is equal to 1, which it is here, then this negative 2, I'll have negative 2 times 1 or negative 2. Okay, so this part at the end doesn't always happen. I don't always have a point to give it. So if it feels like you did everything twice, it's because you did, right? So what we were finding in this particular problem is the slope of the tangent line. It's also called the slope of the curve. That's what I referenced. And there's one other name for it that we're going to encounter today, and it's actually called the derivative as well. So the definition of derivative, and I will tell you right now that much like on the first test, you will be asked to memorize this for exam number 2. And it's like half as long as what you just did on exam 1. So that's a good thing. The definition of the derivative of the function says that the derivative of f at x has a name now. Its name is f prime. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Same thing that we just looked at on the previous screen, provided the limit exists. And again, I'll show you when that actually doesn't happen later. Hang on, sorry about that. Cut that out. And this is for all x for which, I think there's a typo in my notes. Does it say for all x or which in your notes too? For which, so it's fixed under your notes, but I didn't get fixed in mine. Okay, for which this limit exists. f prime is a function of f. So for those of you who have heard of or seen derivatives, this is actually what a derivative is. It is the slope of a tangent line, or slope of the curve. Now, we're going to learn lots of really great things, and some of you probably have even seen some of the great things we're going to learn in the rest of Chapter 2. But in Section 2.1, we are going to use the limit definition of derivative. Okay? So it's kind of like when a child is first learning to multiply, it is far more common right now for them to understand multiplication as repeated addition. So the first thing that they learn when they learn to multiply is they don't learn that 3 times 2 is 6. They learn that 3 times 2 is 3, add it to itself 2 times. And they do that sort of the long way, and they do it with pictures and things like that. This is something akin to that. It's understanding the meaning behind what in the world do these derivatives do anyway, besides just having a whole bunch of rules that I can apply. Okay, this is what's going on. It's finding these slopes. So we're going to do several examples of these. You'll notice on example number 2, as opposed to, say, example number 1, I'm not given the 0.0, like this one's giving me the 0.15, right? I'm not given a point on number 2. Sometimes you are and sometimes you aren't, okay? So on this one, it just wants you to find the limit, find the derivative with the limit process. So if it's okay with you guys, I'm going to do the 4 steps, because that's the way I like to do it. That's my preference. But if you want to do it the way I did the first time with the limit on all this stuff, you are welcome to do so. So if we do step number, let me actually write it out here to the side. It's f of x plus h minus f of x over h. And I have the limit as h goes to 0 at the beginning. And because I now have the notation of what this is called, f prime of x, I'll write that in as well. So this is what we're calculating. But we're doing step 1, and step 1 is f of x plus h. So I take the equation I'm given, which is 1 over x squared, and I replace the x with x plus h. So 1 over x plus h squared. I've seen x plus h squared, and we're going to see it over and over and over again, so you're probably not going to have to write it out very many times before you simply remember that this is x squared plus 2xh plus h squared, and every single time it will be. So that's step 1. Step 2 is to take that f of x plus h and subtract f of x. So I have 1 over x squared plus 2xh plus h squared minus 1 over x squared. Now that's not very friendly looking, and the reason it's not is because I'm trying to subtract fractions, and what do you notice about those 2 fractions? They do not have the same denominator. And in order to combine fractions, I need the same denominator to do that. And these denominators, while they look like they have an x squared in common, they don't, because x squared's a term in the first denominator, not a factor, right? So the thing that we have to do, the only thing that can be done, and I'll shift so I have some more space, is to simply multiply the 2 denominators by one another. So the first one gets multiplied by x squared, the second one by x squared plus 2xh plus h squared. Resist the urge to distribute. That will not help you out in this particular problem. We want to leave that denominator in factored form. So my new denominator that I get when I do this really just needs to say x squared times x squared plus 2xh plus h squared. Just like that. The numerator will have some pieces that will consolidate. I have x squared in the first one, right here. And this one will just be the negative of each of these things, right? There's a negative here, and then I have x squared plus 2xh plus h squared here. So it's just going to negate everything. So I have minus x squared minus 2xh and minus h squared. So what do we see reduce? The x squareds reduce. And when the x squareds reduce, what do we notice about the h's? There's an h and everything up on top, right? Like that. We're going to need that in a minute. We aren't there yet, but we are going to need that in a minute. There's one other thing that you might actually, hang on. Is this step done? I think this step's done. So we're about to get to the H step. I was thinking I need to do one more thing before that. So as we're taking a look at this then, we have the ability to notice that these H's are going to reduce. Yeah, that's where I was. All right. Step number 3 then is to take that expression, f of x plus h, minus my f of x over h now. So while it is true that I'm going to take all of this and divide it by h, that's not a very particularly pretty thing to write down because it's fractions divided by fraction. Well, a fraction divided by something. So I have this piece that I already had. But instead of dividing by h squared, I'm going to multiply by the reciprocal of 1 over h. Right? Division is the same as multiplying by reciprocals. That's an algebra fact that I hope that you remember. It's a very helpful one here. Because what you see is those h's that are present in the numerator, like I mentioned a moment ago, have the ability to cancel with the h that's now in that denominator for the reciprocal. So this h in the denominator will cancel with one of each of these h's in the numerator. So what does it leave me with right now? Let's see. I have negative 2x from right here. And I have minus 1, right? Or sorry, minus h from right there. And then I have x squared times x squared plus 2xh plus h squared. And it might not feel like that's a whole lot better, but it actually is, because we're about to plug in 0 for h, and there's a lot of h's still in my problem, right? So a lot of these pieces are going to disappear in the next step. So, do I have another slide or do I not? I do not. Let me actually slide this up a little, see if I can finish the bottom. Step 4 then, last step. The limit step. The limit as h goes to 0 of f of x plus h minus f of x over h is the limit as h goes to 0 of what we got in step 3, namely negative 2x minus h over x squared times x squared plus 2xh plus h squared. And at this point, there's nothing wrong with me putting zeros in for h's because I no longer will get a 0 over 0 kind of thing that happened before, right? So this leaves me with negative 2x because this h becomes 0, this h becomes 0, and this h becomes 0, right? That's a bunch of h's becoming 0. You have x squared on bottom times x squared plus 2x on bottom. Oh, no, I'm sorry, just x squared on bottom. I didn't highlight all of it, so sorry. All of this becomes 0 because it's multiplied by 0. So this x squared remains, this x squared remains because everything after it's addition. So I have negative 2x on top and x to the 4th on bottom, but that should reduce to what? Right, negative 2 over x cubed. One of the x's will cancel in the top and in the bottom. So I've shown you how this limit definition works for a quadratic. I've shown you how the limit definition works for a fractional piece, right? Something that's a rational equation. And now we're going to do the same thing for a radical equation, but the directions change a little bit. Part A is the same directions we've been doing. I'm sorry, it's not. I take that back. It still combines some things. The first step we're going to do in finding what we're looking for here is the same thing we've been doing. We're finding the slope of the tangent line. Step A actually asks us not just to find the slope of the tangent line, but to find the equation of the tangent line. So an equation actually has a couple of different forms. So y equal mx plus b, that's one of them. You might remember y minus y1 equals m times x minus x1. That's another form. But I think you're going to see something happen in this that's quite familiar, namely that you've seen happen before. So we're going to use that same 4-step process. So step number 1 is to find f of x plus h. And I don't have a whole lot of simplifying. It's the square root of x plus h. not much to do, okay? Step 2 is to find f of x plus h minus f of x. And there's not a lot of simplifying here either. It's the same f of x plus h I had from step 1 minus the original equation, square root of x. Step 3 looks like taking all of this and dividing it by h. So, okay, I have square root of x plus h minus the square root of x over h. And at this point, you should still be saying, well, there's nothing I can simplify, but we have simplified something like this before. Do you remember what we did? We did. We rationalized the numerator. And we did those limits problems like that because this was coming up, and we were going to do it again. So that's what we're going to do. We're going to multiply by the conjugate on the top and the bottom. So the square root of x plus h plus the square root of x on the top and on the bottom. And if you'll remember when we did this on the bottom before, we don't actually want to distribute. We really want to leave it again in factored form, much like the last problem, really. But the numerator is the part that cleans up, right? We're rationalizing the numerator because we want the numerator to actually simplify. So when we distribute out the inner and the outer terms, they're identical and they add to 0. It's just the first terms we get and the last terms. And of course, they are purposefully created so that the square roots eliminate. The first term times itself is just x plus h. The sign stays negative in the middle, and the last term by itself times itself really is just x. And then what do you notice happening on top? Yep, the x's cancel, leaving me with h. And there's an h on bottom as well. So if you want, you can reduce this here as long as you remember that as you do so, you're reducing the numerator to have a value of 1. So you actually end up getting 1 over the square root of x plus h plus the square root of x. That's what we actually have at this particular point. And we're not done because this is step 3 and I'm supposed to do 4 steps. So let me actually move up to here because I think I will have space over here. We'll do the limit as h approaches 0 of f of x plus h minus f of x over h. So this is the limit as h approaches 0 of my function in step 3, right? Which is 1 over square root of x plus h plus the square root of x. So we see happening here, this is too much going on. There we go. What we see happening here is that this h right here becomes 0. And then what happens in the denominator is that there's 2 identical pieces of things, right? So we have our limit as h goes to, I'm sorry, I don't need that anymore. I'm putting in the zeros. I apologize. We have 1 over, and then we have the square root of x plus 0, or you could just write square root of x plus the square root of x. So this becomes 1 over 2 square roots of x. And while it may feel like, this is the derivative, while it may feel like, oh, I need to rationalize the denominator, you do not. And the reason that you do not is because that denominator, whether it's rational or irrational, depends on the value for x. If x is a perfect square, like say 4, then it's already in rational form. If it's not, like say 3, then you'd have to rationalize that particular value. So check it out real quick. Our last piece then is to create that equation. This is my value for x, so I'm finding f prime of 1. So this is 1 over 2 square root 1, which is going to give me 1/2, you bet. And then I'm going to choose to do y minus y1, which they gave me as 1, equals the m value I just found, which is 1/2, times x minus the x value they gave me, which is 1. I'm going to use the point slope form to create my line. And then I need to simplify it to say y equals. I don't think I have another space. I do have another space. Excellent. So as I simplify this, we'll distribute our 1/2 through. So y minus 1 equals 1/2 x minus 1/2. We'll add our 1. Negative 1/2 and positive 1 ends up giving me a 1/2 x plus 1/2. That's the slope of the tangent line. Part B talks about a graphing calculator interpretation, and I'd like to sort of just sketch for you what you'll see, because I know you can put these equations into your calculator. What it's wanting you to put into your calculator is the original equation, f of x equals square root of x, and your line that you created. And if you do that, here's what will happen visually in your calculator screen. The graph of the square root of x looks something like this. Agreed? And the 0.11 is somewhere about right here. And what will end up happening if you create the line, at the tangent line, visually, from what you just got, is you end up having, okay, and I'll shift my line because I can't get my lines to do what I want it to do today. You end up with this line. And this is the line your calculator will show. It won't show in colors for most of your calculators, but it'll show you the line, and it'll show you this curve. All right, we have this tiny little bit more of things to do, but we will finish it next time. I would encourage you to start the homework because we've done almost everything you need for the homework, and we will finish this section and the next one on Wednesday, which means on Friday you'll have both 2-1 and 2-2 due. So I strongly encourage you to start 2-1, get most of it done. You'll know when you get to the point where you're stuck, and then just stop there, okay? Have a great couple days, and I'll see y'all on Wednesday.